Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Level Chemistry Unit 3 for October 2019. Let us begin with the first part. Question 1. A series of tests is carried out on a solid compound A and an aqueous solution B. Compound A contains one cation and one anion. They want you to complete the inferences. A flame test is carried out on A. The observation is a yellow flame. Of course, when we see a yellow flame, it's indicative of sodium cation. So the answer here should be sodium cation. So the cation in A is sodium. Then they say a small amount of solid A is placed in a test tube and heated strongly. Every time you see something about strong heating, that could be thermodecomposition. So they say a glowing splint is held in the mouth of the test tube. In the observation is a glowing splint relights. Oxygen is the only gas that relights a glowing splint. So here when they ask the gas form, that should be oxygen gas. And the formula of the anion in A, of course at international A level, the only anion that is going to bring out oxygen is going to be a nitrate. Remember, this is thermodecomposition of a nitrate. And since this is a group 1 nitrate, it's sodium nitrate, it should be able to produce oxygen as well. Remember, thermodecomposition of a nitrate with a group 1 or group 2 will produce oxygen. So moving on. Part B, they say, a series of tests is carried out on aqueous solution B. They want you to complete the inferences. A piece of magnesium ribbon is added to 5 centimeters cubed of B in a test tube. Of course, magnesium is a metal. So they say a lighted splint is held over the mouth of a test tube. Using a lighted splint is to test for presence of hydrogen. So I wrote a formula for you here. If we have a metal like magnesium ribbon plus acid, we expect to get salt and hydrogen. So here the observation, they say bubbles of a gas are given off and the gas burns with a squeaky pop. So if you get a metal, you add acid to the metal, you get a salt and hydrogen gas. We test hydrogen gas by using a lighted splint. If it burns with a squeaky pop, then that is hydrogen gas. And therefore the cation in the sample was H+, because all acids have H+ as the cation in them. Command 2 says silver nitrate solution acidified with dilute nitric acid is added to another 5 centimeters cubed of B in a test tube. The observation is a white precipitate. Every time a combination of silver nitrate and nitric acid are added to a sample and a white precipitate is observed, that precipitate should be silver chloride. Here they asked us for the name or the formula of the precipitate. It is silver chloride precipitate. And the name or formula for solution B, it should be HCl, because remember in solution B we observed the cation is H+, and we have observed the anion is Cl-, so it should be HCl. That is the acid that was added. So this brings us to the end of question 1. Let's continue to question 2. Question 2, tests are carried out to identify 3 organic liquids. There is C, D, and E. A spatula measure of phosphorus pentachloride, PCl5, is added to each liquid in separate test tubes. The gas given off is tested with damp low litmus paper. If you're testing a gas with damp low litmus paper, then you want to know if it's an acidic gas. The first observation for C, we see misty fumes are given off. Because they added PCl5 and we observe misty fumes, that should be HCl gas. They also further go on to say damp low litmus paper are turned red. This is an indication that the gas produced is acidic. Then with D, they say misty fumes are given off. That is HCl as well. And damp low litmus paper turns red. That is confirmation of an acidic gas. Here there is no change. Now we need to go back and observe. This experiment used PCl5. We know that PCl5 is used to test for presence of OH group, whether in carboxylic acid or in alcohol. So the observations we see here tell us that C and D could be an alcohol or a carboxylic acid. However, E does not have OH group because there was no observable change. Down here they say identify by name or formula the misty fumes produced by the liquid C and D. Of course, that is hydrogen chloride. Part B says 2 centimeters cubed of aqueous sodium carbonate is added to each liquid in separate test tubes. Any gas given off is tested with lime water. When we test a gas with lime water, if the lime water turns milky or cloudy, the gas we are testing for is carbon dioxide. And we also need to know that sodium carbonate is used to test for presence of a carboxylic acid group. So let's see the observations. They say with C, bubbles of a colorless gas are given off and lime water turns milky. This is a confirmation that C is a carboxylic acid. But we see with D there is no observable change when sodium carbonate is added, yet we observe from above that D had OH group. So because D has an OH group that is not a carboxylic acid, it should therefore be an alcohol. With E, there is no observable change, of course, as well. So here they say identify by name or formula the gas produced by liquid C. That gas is carbon dioxide. Let's go on. Here they say each of the compounds C, D, and E contain 3 carbon atoms and 1 functional group, which is on the end of the carbon chain. Using this information and the results from part A and B, deduce the structures of C and D. Now we know C is a carboxylic acid. It means we need to write a carboxylic acid that has 3 carbons, and that is going to be propanoic acid. Also, we observe that D is an alcohol. We need to write an alcohol that has only 1 functional group, and the OH is at the end. So it's going to be propan-1O, which is the primary alcohol. Part E says the mass spectrum of E has a molecular ion peak at mass to charge 58. Using this information and the information in C, deduce the structure of E. From C, we have observed that E has 3 carbons and it has 1 functional group at the end, yet it's not an alcohol and not a carboxylic acid. The only structure that has a molecular ion at mass to charge 58 with 1 functional group at the end is an aldehyde, so I draw this structure, which is propanal. Here they say give a chemical test and positive results to confirm the identity of the functional group in A. Because this is an aldehyde functional group, you can use Benedict or Fehling solution, and if a red precipitate is observed, that is confirmation for that. Or you could use Tollens reagent, and if a silver mirror is observed, that is confirmation that is an aldehyde. Now be very careful, this information is not included in the new syllabus textbook. However, it's examinable, so put great emphasis on remembering this part of the experiment. Here they say the apparatus shown was used to find the enthalpy change of combustion of one of the liquids C, D, and E. We see they have a thermometer, they have a starter, they have a clamp, beaker, water, and a spirit burner. They say list all the measurements you would make in carrying out this experiment. So in carrying out this experiment, you have to measure the mass of water, because in your Q is equal to MC delta T, this calculation. You will need to know the mass, and we know the mass using the volume of the water. Remember, density of the water is assumed to be 1 gram per centimeters cubed. And then if we know the volume, then we approximate the total volume to equal to the total mass. You also need to calculate the temperature, initial and final temperature, so that you can find out the delta T. You also need to know the mass of the fuel used in the combustion. So here I said, measure the volume of water, measure the initial and the final temperature of the water, measure the spirit burner at the start and at the end of the experiment. The reason for measuring the spirit burner is to find the mass of the spirit burner before you burn any fuel and the mass of the spirit burner after burning the fuel, so that we can find the mass of the fuel that has been burnt. Down here they say, give 2 ways other than changing the measuring instrument or repeating the experiment in which the accuracy of the results using this apparatus could be improved. If you look at the setup here, there is going to be a lot of heat loss to the surroundings, so we need to put a drought shield. We need to cover here at the top, put an enclosure at the top in order to ensure that we minimize heat loss. You need to put a drought shield like that. Create insulation in order to minimize the heat loss to the surrounding. And instead of using a beaker, use a copper can, because a copper can is going to have greater conduction in order for all the heat released here to be transferred to the water. So down here I wrote, by adding a drought shield around the apparatus to create insulation, by using copper in the place of a glass beaker, because of course we know copper conducts better, and by placing a lid on the beaker to prevent heat loss. This brings us to the end of question 2. Let's continue to question 3. Question 3. An experiment is carried out to determine the formula of an oxide of copper. A sample of copper oxide is reduced to copper by hydrogen gas using the apparatus shown. So here we can see there is a sample of copper here. It could be copper 1 oxide or copper 2 oxide. Hydrogen gas is passed through as the sample is heated, and then a reduction process occurs, and then the excess hydrogen is burnt off as it leaves the test tube. So down here they say the procedure is weigh the empty test tube, place 2 spatula measures of copper oxide in the test tube and reweigh, then pass hydrogen into the test tube, and after a delay of a few seconds, light the gas at the hole at the end of the test tube. So in step 4 they say start heating the copper oxide, and after the copper oxide has been completely reduced, turn off the Bunsen burner but continue to pass hydrogen over the product until it has cooled. Step 6, weigh the test tube and copper. So in A they say give a reason why in step 3 there should be a delay of a few seconds before lighting the hydrogen at the end of the test tube. I say to ensure that oxygen is completely removed out of the experimental setup, these avoid hazardous explosions. Moving on. So the table of results is as we see here. We have the mass of the test tube, the mass of the test tube and the copper oxide, the mass of the test tube and copper, the mass of copper in the copper oxide, and the mass of oxygen. So to find the mass of copper in the copper oxide, we had to get this, because this is the mass of test tube and copper. When we subtract mass of test tube, we get the mass of copper, which is going to be, so here we have 42.79 minus 40.27. That gives us the mass of copper. The mass of oxygen is going to be the mass of the test tube and copper oxide minus the mass of the test tube, which will give us the mass of the copper oxide. And if we subtract the mass of copper in the copper oxide, we'll be able to get the mass of oxygen, which is 0.63. I showed you what we have to do here and there as well. So next they say use these results to calculate the formula of this copper oxide, and you must show you're working clearly. So beginning with copper, I use the mass of copper, which I calculated here, and the moles of copper should be this mass divided by the atomic mass, and the answer is 3.9685 times 10 power negative 2. When I went to oxygen, the mass is calculated here, so mass divided by atomic mass gave me that as the number of moles. The next part was for me to find the mole ratio of copper to oxygen, which gave me that to that. The answer was 1 to 1. So the formula of the oxide of copper was copper to oxide, which is written as that. Moving on. Here they say the experiment was repeated. However, in step 5, both the Bunsen burner and the hydrogen supply were turned off while the apparatus cooled. State how the appearance of the solid in the test tube changes as the apparatus cools. The color of copper is pink red. However, if the flow of hydrogen is prevented from passing through the test tube as the apparatus cools, it means oxygen is going to come in and oxidation of copper can occur. Now, since we already know this is going to be copper 2, we'll observe a black solid. So here I said the red-pink solid turns black. That is going to be due to formation of copper to oxide. Explain how this change in the procedure affects the calculated formula of the copper oxide. At the end, we will expect that the solid present inside the test tube should only be copper. So if some copper oxide exists, it means the mass of copper that is going to be assumed is going to be higher than it actually is. I say the results would show that more copper is present, or you would assume less oxygen is lost because some copper has been reoxidized back to an oxide, meaning the oxygen that comes in as the flow of hydrogen is prevented is going to lead to an increase in the mass of the contents within the test tube, and therefore the presumed mass of copper is going to be higher than it actually is. Question 4. An experiment is carried out to determine the molar mass of a solid acid H2X. Describe how 250 centimeters cubed of a standard solution should be prepared using a pre-weighed sample of 1.13 grams of H2X. In the first step, dissolve the 1.13 grams of the solid into a beaker with deionized water, and then you transfer the solution into a clean 250 centimeters cubed volumetric flask using a funnel, and ensure that you transfer the washings as well. Then you will add the ionized water to the volumetric flask until the 250 centimeter cubed mark, and then you stop at the volumetric flask and shake to create a solution of uniform concentration. That will be your standard solution. Part B says 25 centimeters cubed of this H2X solution was pipetted into a conical flask and titrated with 0.213 mol per decimeter cubed sodium hydroxide solution. The equation for the reaction is as we see here. So they say the indicator used was phenolphthalein. State the color change at the end point. At the end point, the color is going to change from colorless to pale pink. This is because sodium hydroxide was the one in the B red and the H2X solution was the one in the conical flask, so the color would change from colorless to pale pink. Here we have the results of the titration. They said using appropriate titrations, calculate the mean titer. In order to calculate the mean titer, we need to use concordant results. Concordant results are results which are within plus or minus 0.2 centimeters cubed of each other. So when we see this one here, these two are concordant because the difference between them is within the plus or minus 0.2 centimeter cubed range. So I use 11.90 plus 11.70 divided by 2. We divide by 2 because there are two values we have chosen to be 11.80 centimeters cubed. You have to ensure that as you're writing these values, you leave to 2 decimal places as they have written in the table. The next part, calculate the number of moles of H2X in the 250 centimeters cubed of the solution. We know the number of moles is concentration times volume, and we were given the concentration, which is 0.213. The volume we have calculated is 11.8. We divide this by 1,000 to convert this into decimeters cubed. Those are the number of moles of the sodium hydroxide. And then the next part is to use the mole ratio of the acid to the sodium hydroxide in order to find the number of moles of the acid in 25 centimeters cubed. So since the mole ratio of the acid to sodium hydroxide is 1 to 2, the moles of the acid in 25 should be 1/2 times the moles of sodium hydroxide, and that gave me those moles. Remember, this is in 25 centimeters cubed. However, I need to use this to find the number of moles in 250. So the moles of the acid in 250 are that times 10, so which gave me 1.2567 times 10 power negative 2 moles. The next part, calculate the molar mass of H2X using your answer in B3 and the mass of H2X given. This is quite easy. We know that molar mass should be mass divided by the number of moles. Since I have the mass, which is 1.13 grams, and I have the number of moles, which is 1.2567 times 10 power negative 2, I divided and got 89.9 gram per mole, or you could round off to call it 90 gram per mole. Here they say the maximum uncertainty each time a burette is read is plus or minus 0.05 centimeters cubed. Calculate the percentage uncertainty in measuring the 11.70 centimeters cubed of sodium hydroxide used in titration 3. So in titration 3, we used 11.70. If you go back to the table, we know that the burette is read twice, so 2 times that, divide by that times 100, gave us plus or minus 0.855%, which is the percentage uncertainty. The percentage uncertainties in the 3 titrations are similar. Suggest how the percentage uncertainty in a burette measurement could be reduced without changing the apparatus, and justify your answer. We could reduce it by measuring greater volumes or larger volumes. So here I said there is less percentage error if larger volumes are measured. So what we have to do is to increase the mass of H2X so that there is more moles of H2X in the conical flask, and that would require a large volume of sodium hydroxide from the burette. So here I say, so use more mass of H2X so that a large volume of sodium hydroxide is used from the burette for this reaction. This brings us to the end of question 4. Let's continue to question 5. Question 5, limonene, an oil, can be extracted from oranges in 4 steps. In step 1, grated orange peel is added to some distilled water. The mixture is heated under reflux for about 10 minutes. Draw a label diagram of the apparatus used to reflux the mixture. Here they wanted you to draw the refluxing condenser as well as the apparatus where the sample is heated. So I drew a boiling tube, we can see here, with the orange peels and the solution, the heat source here, and then I positioned the condenser vertically with cooling water coming in at the bottom and water going out at the top. Remember, the top of the condenser should be left open. If you close it, you will lose marks for that. Moving on. Part B. In step 2, the mixture from step 1 is distilled. The distillate contains a mixture of limonene and water. In step 3, the limonene and water mixture from step 2 is poured into a separating funnel and pentane is added. Limonene is much more soluble in pentane than in water. The density of pentane is 0.626 gram per centimeter cubed. They want you to complete the diagram of the separating funnel by drawing the aqueous and pentane layers and labeling them. Here we need to look at the density of pentane given. It is 0.626 gram per centimeter cubed. However, the aqueous layer has a density of about 1 gram per centimeter cubed. It means water or the aqueous layer is denser than the pentane layer, so the organic layer is going to be at the top and the aqueous layer is going to be at the bottom. So this is my diagram here. Next, they say, describe how the separating funnel is used to obtain the pentane layer. The key thing here is to stopper the neck of the funnel and invert in order to shake. That is after adding the pentane layer. So you will shake, slowly opening in order to release the pressure, and then allow the separating funnel to stand so that the 2 layers can reform again. Run off the lower aqueous layer and pour the pentane layer into a clean container. Because limonene has higher solubility in pentane than in water, shaking ensures that the limonene in the aqueous layer has greater exposure to the pentane layer in order for it to leave and move into the organic layer. Moving on. Here they say in step 4, the pentane is allowed to evaporate in a fume cupboard, leaving limonene. 150 milligrams of limonene is produced from 23 grams of orange peel. Calculate the percentage of limonene by mass extracted from the orange peel. Since 1 gram is equal to 1000 milligrams, it means 23 grams should equal to 23 times 10 power 3 milligrams. And therefore, the percentage by mass should be 150 milligrams divided by 23 times 10 power 3 milligrams times 100. And that gave me this. And I rounded off to 3 significant figures to give me 0.652%. Down here they ask, 0.001 mole of limonene decolorized 0.32 grams of bromine water. Explain what these results tell you about the structure of limonene. I know the moles of limonene, but I need to find the number of moles of bromine that was decolorized. Number of moles of bromine in 0.32 grams is 0.32 divided by 160 we have here, which gave me 0.002 mole. So the ratio we have is 0.001 to 0.002, which is going to be a 2:1. Therefore, there will be 2 carbon-carbon double bonds in limonene because 1 mole of limonene uses up 2 bromine molecules. So this brings us to the end of this video as well as the end of this paper. Thank you for being with us. Please do not forget to subscribe. See you in the next video. Bye-bye.